So I'm very excited to see so many people back for the second part of the virtual workshop. I hope it's been informative and useful to all of you so far. I did want to pause for a moment and check to see if we had any questions, particularly maybe like higher level questions or vision type questions that might be appropriate to ask Dr. Liu. Do we have any such questions? Well, that's okay. If we do have further questions during the workshop, we can pick them up. So I think now, without any further ado, I will move now into a short PowerPoint-based introduction of PyCalphad, discussing just a little bit more of the technical details, and then we will return to the MGF cloud environment and ensure that we can continue on with the PyCalphad exercises and interactive demonstrations. So now I will share my screen. Okay, and so I'm Richard Otis. I'm from the Materials Genome Foundation, which co-sponsored today's virtual workshop and provided the cloud infrastructure. And I'm excited to give you a bit of an introduction to the PyCalphad software package. So as Dr. Liu mentioned, PyCalphad is Python-based software for designing thermodynamic models, calculating phase diagrams, and investigating phase equilibria. So it's a CalFad tool, if you're familiar with the CalFad method. And so you can compute all sorts of interesting things that are related to the underlying thermodynamics of a material. That includes things like phase transition temperatures, like melt temperatures, phase fractions, solidification, degradation, corrosion. Basically, just if it's connected to some kind of a chemical process, PyCalphad can help you to model it. And then another important element to know about PyCalphad is that it is a free and open source software package that you can find at pycalphad.org, which contains installation instructions. So I wanted to touch on a few more reasons why you should consider using PyCalphad, things that I think make it special or unique among the other alternative CalPhad-based software packages. So one is the fact that you can build custom Gibbs energy models. So what that means is if there is a new type of physics or new state variable that you'd like to be able to consider within the CalPhad type framework, but it's not something that is supported or yet accepted, perhaps because you're developing it for the first time and working on proving out the concept. PyCalphad can be used to actually develop that energy model and then incorporate it into the regular CalPhad workflow. So you can use it to do things like compute the properties, compute the phase diagram with that custom model, and other things. And we'll touch on a little bit about how to do that today in one of our examples. The other thing that you can do, which is related to the custom energy models, is you can also build custom material property models. So if you'd like to build a CalPhad type model for a material property, but not necessarily just the Gibbs energy, you want to treat perhaps a kinetic property or perhaps something like, we'll touch on an example of liquid viscosity about how to build a CalPhad-based model for that property today. And so that is something else which we claim is a special feature of PyCalphad. Another reason to use PyCalphad is the fact that it's very easily and naturally incorporated into this digital notebook environment. So the Jupyter Notebook or Jupyter Lab, if you're familiar with that. Jupyter Lab is the browser-based interface that we are using today that's providing us access to our Python environment that has PyCalphad installed. Another nice thing about PyCalphad that we make easy is the ability to deploy to cloud infrastructure. So in this case, we have it running on our MGF cloud infrastructure or high performance computing infrastructure. So this is particularly relevant for those of you that might be interested in things like high throughput calculation. And you might discover that with other software codes, there are restrictions due to licensing about the number of devices you can deploy to or the number of cores you're allowed to use simultaneously. Because of PyCalphad's free and open source licensing, there is no restriction on your ability to deploy it to anywhere that that PyCalphad is supported. And then another great reason to use PyCalphad, which is an indirect one, is for database development. So CalPhad-based model optimization, which is performed via SBay, which we will learn about in another session today. So to touch on some notable features in the latest release series of PyCalphad. So this is the 0.8 series. The latest release version is actually 0.8.4, but this 0.8 series kind of touches on a lot of the major things that have happened. So we've made a lot of progress in terms of the performance, and in particular things like the cold start calculation time. So PyCalphad does a lot of work in the background to provide so much flexibility with the models. And we've done a lot of work to eliminate some of the just-in-time compilation that's happening during every calculation, and such that for simple systems at least, the start time will be almost imperceptible, and then even in complex systems, the start time is not too long. We've also added a feature which is primarily due to Brandon Bachland, which is this user-specified reference state capability. So similar to other software packages where you can do a calculation with respect to a particular thermodynamic reference state, we have the ability to express those reference states in Python and to manipulate them. And we'll touch on an example of this. The binary and ternary phase diagram plotting, the type that you usually expect. The ability to specify temperature, pressure, chemical potential, and mole fraction conditions for multi-component systems. We support that. You can do stepping and mapping calculations. We support global minimization, meaning that we have automated miscibility gap detection. So you're always going to find the miscibility gaps, even in complex systems. We also support the associate model and the two sublattice ionic liquid model. And support for ionic solids is on the way, which we hope to ship in the 0.9 series. We also support the standard magnetic ordering models like the Enden-Hillert-Yarl model and the more recent model due to Wei Xiong and collaborators. And then just continuing down the list, order disorder model, two-state model, Einstein model. And there may even be a few that I'm missing here, but just about any of the kind of standard CalPhad models that you might be interested in, particularly for alloy systems, we support. And another thing is that we do ship and support for all three major operating system platforms. So that's Windows, Mac, and Linux. In terms of current limitations, we're still working through more advanced conditions like being able to fix the amount and stability of a phase. So this is really important for things like phase boundary tracing and efficient phase transition temperature calculation in multi-component systems. So we're working on this. I actually hope to have something to announce about that in the the next few months. And then we also have some progress made in the quasi-chemical model. We have an active project going on at Penn State, working on the development of that, and also some more advanced ternary excess models. Now, there's a couple of TDB features that aren't supported yet. If this means anything to you, if it doesn't mean anything to you, that's okay. These options are relatively rare. Things like option B, option F. So these are certain options for specifying only the symmetry independent interaction parameters in certain multi-sublattice phases for BCC and FCC. If you don't know what they are, it's okay. And then some advanced features like status bits, which get a little bit into the implementation details of some other packages. But the important thing is that if you run into an issue where you have a TDB file that you're having trouble running inside of Thermocalc or another software package, you can reach out to us, and usually we can help you work around whatever the issue is. I also wanted to highlight some use cases from the PyCalphad community. So these are papers that have been published by people where none of the co-authors was a core contributor to PyCalphad. So there's been some work published in using PyCalphad to build two-phase elastic constants models. So that was looking at nickel-based superalloys was the application. And so they were able to build a property model where the output was actually dependent on the properties of multiple phases. There's also been some work in exploring CalFad-based interfacial energy prediction for coherent solid-solid and solid-liquid interfaces, which was published last year. That's some work out of CSU in China. And then more recently, there's a preprint available of some work out of Carnegie Mellon University for machine learning enabled by PyCalphad, where they extracted phase boundaries from many TDB files that they had collected from public sources. And so they used PyCalphad to compute the phase diagrams and extract the liquidus surfaces, and then take that data as input into a machine learning model. The idea being that they thought that they wanted to look at the ability to correlate these predicted liquidus surfaces with some other features, some of which are kind of outside of CalFad. So it's sort of a blended approach where they took elements of CalFad, which incorporate physics, and then add in additional information. And so that's kind of the overall view of PyCalphad. I will note that on your MGF cloud accounts, you have a PDF copy of the slides. And so if you have any questions about something you saw or needed a reference, you have that material, and it's available to you. So I'm now happy to take any questions that we might have, if we have them.
Richard, there's a question in the chat.
Okay, so let's see if we can bring that question up here. So can I touch on applications with hydrometallurgy, like leaching minerals, reaction to mineralized rock and an oxidant H2O? So we won't touch on any applications like that in today's workshop. Most of our examples are going to be more traditional metallurgical examples. And part of that is a little bit to do with the simplicity of the systems, which is easier to deal with in the given time. You certainly can use PyCalphad for hydrometallurgy, but as with so many things in CalFad, it's dependent on the availability of the database of interest. And if the database doesn't exist, then it's possible to use SBAY to build it. So what I would say is, for this, we would need to identify the phases that are of interest, and then understand how they would be modeled using CalPhad. And then, and this, I'm speaking a bit out of turn because hydrometallurgy is a bit outside of my usual technical area, but it's certainly possible to do. You would take the information about how the phases have been modeled in the past, or use scientific judgment if they haven't been done before. You would define models for each of those phases. You would collect thermochemical data from the literature, plus potentially performing first principles calculations yourselves or performing experiments yourselves. You would then put that data into SBAY and then optimize the model parameters to build the database. And then once you have that database, you can then use PyCalphad to perform calculations that might be of interest. So as I was answering that question, there are a couple of wrinkles that you would touch on. Additionally, though, that you may be interested in things like steady state reaction rates and things of that nature that go a little bit outside of what we currently have implemented in PyCalphad, but I'd be happy to talk with you in more detail to try to understand what that need is. And so sometimes the nice thing about PyCalphad with the flexibility of it means that if you're already familiar with Python, it is possible to write what is hopefully just a little bit of code wrapping PyCalphad that will enable you to answer the scientific or engineering question that's interesting to you. And I would say that is the case with what I've seen published in the literature so far with these community use cases. Is they are people who used PyCalphad as the CalPhad engine for their problem of interest, and then they wrote some code around it that basically gave it the right inputs and outputs to get the answer that was interesting to you. So, okay. So now we'll go back to our cloud accounts, and
you
we'll
answer the second question there, Richard?
Oh, I'm sorry, I didn't see the second question. Creating a user-defined database for system of interest, is it covered in this workshop? Yes, we are going to talk. So creating databases is the purpose of SBAY. SBAY is the primary model optimization and database building tool that is designed to work with PyCalphad. So, and yes, we will touch on that today. So right after this this section, we're going to go through some examples using PyCalphad. Then we'll take a short break, and then when we return, Brandon Bachland will pick up, and he will walk everyone through SBAY. And so we'll go through some examples, and hopefully it'll become clear how the first principles calculations and the work that you did in the first session are connected to the database building work that we will do today. So you'll see that first principles calculations and CalPhad go very well together, which is one of the messages we hope you will leave with from this workshop. Okay, so I am seeing no further questions at this time. So I will continue with this. So hopefully everyone had no problems logging back in today, and we're back in our familiar Jupyter lab environment. Please leave a message in the chat if you had any trouble logging back in, and we will help you. But otherwise, I will just continue on with this workshop. One thing I will note, which is a slightly different format, is in this case, all of the notebooks in the PyCalphad section here. So we're going into the workshop folder, then PyCalphad. So these notebooks are already completed. There's no fill in the blank sections. So they're designed to run by default. So in a sense, they're kind of already solved. But we will go through them kind of slowly and not just run them and move on. So we'll try to spend a little bit of time talk about some of the details and give you an opportunity to ask questions as we go through. Also note down here at the bottom, we have this this PDF file, which is the slides that you just saw. So they're numbered here because they're designed that we can go in order and talk about them. So the first one that we're going to go through here is a simple example. We're going to show about how to calculate the chemical activity and also how to compare that with some experimental data that we already gathered from the literature. And so in PyCalphad and really any CalPhad-based package, you have to have a database. You have to specify the components of interest, the phases of interest, and the conditions. And so these database files are made by researchers. And after today, some of those researchers may also be you using SBay. And you perform a modeling of the Gibbs energy functions. And those parameters that are fit during this optimization process are stored in the database. And the most common database storage format is this TDB format. And so these files are usually saved with a file extension TDB. And we have defined here this syntax here, this database object, which is designed to read the database files in. And so for the purposes of the workshop, we do provide a couple of different databases here. You can see in this database subfolder. One thing we'll note, and so we don't by default ship any kind of quote unquote official databases for PyCalphad. At this time, we leave it up to the scientific and engineering judgment of the users to determine whether or not a database is appropriate for what they're doing. However, we do recommend as a starting point, particularly for a system that you haven't been working with for a while, we recommend using the TDB-DB. So this is the TDB database. It's an indexing service which is provided by Axel van de Waal at Brown University. You can use this to search for TDB files. And so I'll just show you real quick. So for example, you could type in cobalt chrome, and it will provide a listing of files that were found from the literature. So the link to a publication, usually, if it's from a peer-reviewed source, and then often also a link to the TDB file. And so this is often a good place to get just a rough sense of the kind of coverage that a particular system of interest may have in the community. And so while of course we don't recommend just blindly downloading a TDB file without checking, we recommend that you take a look at the publication and make an informed judgment about whether or not it's appropriate. But this is often a great place to start and find out what's out there and move on from there. And so we'll now continue on with this example. So in this case, we're looking at the aluminum zinc system. So this is a binary system. And what we're going to do is we're going to compute the thermodynamic activity at a particular temperature for this system, and we're going to compare it to some experimental data. So this is some tabulated mole fractions of zinc and activities of zinc, which were collected from this paper here above, which you can go and review from some time. And one of the important things to note is you'll see that the reference date here is pure zinc at that particular temperature. So you have to remember that when computing activities and comparing activities in particular, the reference date is important, and we'll touch on that a little bit later. And so we have our experimental data, which we've just manually tabulated for ourselves. So that'll help us later. And now we're going to set up the calculation. So if you're familiar with Python, there's not anything fancy going on here. So from PyCalphad, we're importing the database object. We're importing a function named equilibrium. So we're going to be introduced to the equilibrium function, just a short time from now. And then we also import the object or the module variables, which defines our things like our temperature and our pressure. But writing variables is all the time is sort of tedious. And so we use this syntax variables as v to rename the module in our local context to just v. So we only have to write v to talk about variables. And so next we go through and we define our database object. So here it is going to tell PyCalphad to load the database that's in this in our database folder, which is for aluminum zinc. You can see the TDB file there. And so we'll just run this first cell, which we can do with shift enter recall from yesterday's session. And so we've run and imported the database. We've defined our components. We've defined our phases. So the syntax here is a common pattern in PyCalphad where we need a way to write. We want to consider all of the phases that are in the database. And so the database object, which I will show you now. The database object has a number of methods defined on it. So things like elements will tell us all of the elements that are in the database. If we write phases, this gives us a dictionary containing the names of the phases and then a phase object, which defines the sublattice model for that phase, and also some other important metadata. And so if we write phases.keys, we can see we get a list of all the phases that are in the system. And so this is a common pattern used in PyCalphad for when we want to say, I want all the phases, but I don't want to have to write them all manually. So this is one way to do that. So now we go through and again, an activity calculation requires a reference state. So what we're going to do here is we're going to compute equilibrium at our reference state. So we say pure zinc at our desired temperature, which here is 1073 Kelvin. So all units in PyCalphad are in SI units. So Kelvin, pascals, and so on. And so we define our equilibrium, which uses this syntax where we specify the database, the components, phases, and then a dictionary of pressure, temperature, and mole fraction. Another thing to note is that it's implicitly here n equals 1. And so you can also explicitly write n equals 1, although you do not have to. So we've performed our calculation. It gave us a warning about a normalization issue, which is just comes from the fact that we calculated at a pure zinc here. And then next, we're going to do our calculation over the entire composition range. And notice it's almost the same syntax as before, except we're saving the result as a different name. And instead of writing pure zinc now, we wrote this tuple here. And this tuple has 3 elements. So it has the starting point, the finish point, and then the step size. So it's start, stop, step is what the syntax means right here. And so this is what's going to give us all of the activities that we need to compare to the reference state. And so now we need to compute the activities. And so we use the thermodynamic definition of the activity and the relationship to the chemical potential. And so we extract the chemical potential of zinc from each of the equilibrium calculations. And we'll in the third module, we talk a little bit more about how to actually interact with the results. But here, just quickly, you can see how we extract the chemical potentials of zinc for each of these calculations. And then for NumPy, for the activity, we just apply the thermodynamic definition, where we have the chemical potential difference. So the chemical potential minus the chemical potential at the reference divided by R times T. So 8.315 here is approximately the gas constant. So we run that, and now we have the activity. And then finally, we'll plot the result. So this last step here is just some matplotlib uh, uh, working with the arrays from the results. So we have here the chemical potential, or sorry, the mole fraction of zinc, and then the activity of zinc relative to the reference state. And then as a scatter plot, we plot the experimental data that we had collected from the literature before. And then finally, we plot it. And so you can see here, as you would expect, since this particular CalPhad database was published well after the work of Yazawa et al., that it's consistent. The prediction is consistent with the experimental results. So that's kind of the basics of equilibrium calculation and working with the result of a calculation. And so next we'll go into binary phase diagram calculation. I'll pause for a moment just in case we have questions.
Hey, Richard.
Yes.
This is Akapol.
Hey, Akapol, what can I do for you?
Yeah, so I try like use those different step size. Like when I increase the step size to like 0.1, the activity at the 1 completely sync is missing. What happened to that?
I'm sorry, what step size did you increase it to?
So for equilibrium here, yeah, for that one, yeah, I added to 0.1, just 0.1, change to 0.1, yeah, and then I recalculate everything, and then the plot is like the last part of the plot is missing. Yeah, you can see there the 1 is missing.
Yeah.
These are
What happened?
The intervals here are basically NumPy A range, and so they're open intervals on the top, and so it's
okay,
it's
so
going to be
it
from
doesn't actually. So 0.9.
correct.
Up to 0.9.
Yep.
Okay. Okay.
Yeah. So that is a it's I would call this a bug because it surprises the user. You would not expect the interval like that to be dependent on this detail here, but yeah, basically it's because it's checking to see whether or not it's reached the endpoint yet, and so you run into this issue with like what Brandon said with open intervals. So if that does happen, you just slightly have to add some jitter to that step size, and that issue will go away. We will get around to addressing that, making that behave a little bit better in the future.
Mm-hmm.
Yeah, thank you for that question. And so now what I'll do is I'll go to binary phase diagram calculation. And so here, what we're going to see is we have the ability to compute energy surfaces for binary systems. And so the way this works is it is a similar sort of setup to the equilibrium calculations, except now we're importing this function called calculate instead of equilibrium. And the reason for that is because equilibrium is for equilibrium properties and calculate is for non-equilibrium properties. So that's sort of how it's broken up in terms of responsibility inside of PyCalphad. And so what I'll do is just to show you the idea, I'll run the result and we can discuss it. And so this is an energy surface in the niobium rhenium system. So the y-axis is Gibbs energy and the x-axis is the rhenium content of the system. And what we're looking at here is more or less what you'd expect from a this sort of energy composition plot. But I do want to draw your attention to the chi phase. So the chi phase here, which you can see sort of near the 0.6 content here, you'll see that it's actually a multi-valued function. And the reasoning for that is because the chi phase contains internal degrees of freedom. It's a multiple sublattice phase with internal degrees of freedom. And so what that means is there are multiple configurations of the site fractions that will give you the same overall rhenium content. And a special feature of PyCalphad is the fact that we can actually plot all of those metastable configurations, not merely the low energy configuration, which you see defining sort of this convex hull for the chi phase at the bottom here. In PyCalphad, this calculate function gives you the ability to plot the metastable configurations as well, and pretty nicely too. So you can see things like these endpoints here corresponding to the end members for this phase. This phase is a sublattice model, and then you also see sort of these more solid lines. These correspond to the sort of, if you imagine like a square defining the internal degrees of freedom, these are like the edges going between. And so you can see these edges reflecting those binary interactions between the end members. And so you get a really nice picture of what's going on in terms of the internal degrees of freedom in the system, which can be especially helpful as you go to more sublattices and you get more complicated behavior. This gives you some insight into what's happening with those metastable end members. And so the code that's happening up here is primarily for plotting purposes. And so we're calling calculate inside of a loop. And so we're calling one phase at a time and then plotting the results as a scatter plot. And so this gives us the color-coded legend that we're after here, since calculate itself does not support natively like a color-coded legend as an output. So that's the energy plotting capability in PyCalphad. Next, we'll talk about the phase diagrams, so binary phase diagrams. And so this is using a function called benplot. And so benplot leverages the calculate and equilibrium functions under the hood to map out the phase diagram for a binary system. And so the way that we call benplot is similar to the way we call equilibrium. So we call database the components, the phases, and then a dictionary defining the conditions. Except in this time, remember, since it's a two-dimensional plot, we need to define a step over the x-axis, the composition of zinc, as well as temperature. So here, notice we have start, step, start, stop, step for both the mole fraction and the temperature. So in this case, we have 300 to 1,000 Kelvin stepping in 10 Kelvin increments. And then this keyword argument back here is just a little bit like an intermediate level feature, which enables you to customize the plot a bit more. So in this case, we wanted the ability to define the size of our figure from matplotlib. And so we wanted to specify sort of this 9 by 6 size for the figure. And so benplot doesn't have its own figure size functionality. We leave all of that to matplotlib. But so all you do is you just pass in the object that you want benplot to draw into, and it will do the rest. So this gives you a lot of control. So you can leverage all of the matplotlib advanced style and customization capabilities without PyCalphad needing to know anything about it. And so we'll run that calculation now. So aluminum zinc is a pretty simple system, so the calculation runs quickly. And so you can see here the familiar low temperature FCC miscibility gap, the expected invariant reaction between FCC, HCP, and liquid at the high zinc in the zinc rich region, as well as the expected liquidus and solidus surfaces. So we can also treat more complicated systems. So like the copper oxygen system, we are interested in this system here, which has a 2 sublattice ionic liquid, which is a slightly more complicated setup. So this is, in this case, we're getting a warning because the TDB file is not quite formatted correctly. You'll sometimes encounter this with particularly older TDB files from the literature. Sometimes they will have type definitions that aren't fully defined. There's usually no, there's often no impact to the calculation result, but it is something to be aware of and something to investigate if you get a warning. And so this is the copper oxygen phase diagram here. And so we can see the strong role that the ordering, the short range ordering in the ionic liquid is having on the system. So note, in this case, this is not a full range phase diagram. So this goes from pure copper to about 0.6 mole fraction of oxygen. And so we can see this, so we can see a miscibility gap here that is expected, as well as this, this copper oxygen phase, which goes up to a bit higher temperature also. And so the main thing that this is meant to illustrate is the fact that we also have the ability to consider charged species inside of PyCalphad. Currently just the 2 sublattice ionic liquid model, but in the not too distant future, solid ionic solids as well. So I'll pause for a moment to take questions. So I'm seeing none, so I'll continue on to this next part. So this next part is a little bit more wordy and documentation heavy, but you're likely to refer back to this one as you're developing codes to actually interact with PyCalphad data. And so this is, in my opinion, one of the most powerful features of PyCalphad, which is the fact that the results of calling calculate an equilibrium are these X-array dataset objects. And so an X-array dataset is it represents n-dimensional tabular data. And so if you've ever used something like a pandas data frame before, which perhaps you have if you've done anything related to data science in Python, this X-array dataset is like an n-dimensional analog to that. And so it's very powerful. It has lots of querying and filtering capabilities that we'll just briefly touch on today. But the great thing is, because this is a sort of a standard object output format, you can refer to dedicated documentation for X-array, which will provide you a lot of information about how to interact with this object in more advanced ways. And so the way that this works is we have 3 key concepts to understand for this data set. We have dimensions. And so these are our conditions that we calculate over. So these are like pressure and temperature. Then we have coordinates. So these are the actual values taken on by the dimension. So coordinates would be like the actual values of the pressure at particular steps that we take, depending on the calculation. Or it might be a point value if it's a point calculation. And then the data variables are the properties that are calculated by PyCalphad. So it's sort of like the outputs of the calculation, like the Gibbs energy, the mixing energy, the internal degrees of freedom, things like that. And so what we have for calculate, so calculate and equilibrium are each, they return slightly different output. And so you get back these 5 different dimensions here. You get pressure, temperature, component, which just gives you the names of the components in the system. And then this internal DOF object, which you get back. And so this gives you the this gives you the site fractions. And so what that provides you is information about the internal degrees of freedom in the phase. So if you call calculate by default, it randomly samples the energy surface of the phase of the phase or phases of interest. And so what you'll get back then is a random sampling of the internal degrees of freedom of the system. And so this dimension gives you a way to index into a particular point, a particular degree of freedom. And then the points dimension is just the number of samples that you computed. And so normally it will be random. So there's not really any underlying physical meaning to the order of the points that you get. But that dimension exists so that you have a way to index into it. And then the data variables you get back are phase. So that's just the name of the phase. So when you call calculate, it's usually just the name of the phase that you passed. So you will usually know that, but sometimes you like to combine multiple calculate results together into one object. And so it's nice to have that indexing if you start doing multiple phase data processing. Then you have X. So X is a mole fraction. So it's the composition of each component. And that's a function of the temperature, pressure, and the points. So, as we randomly sample the internal degrees of freedom, for each of those internal degrees of freedom, we compute the mole fraction, and then we also save that. So we have X, which is the mole fraction, and then the site fractions are saved in this Y data variable. And then the last one is output. And so output is not literally the string output, but it's whatever property you calculated. And so by default, the output is GM, the molar Gibbs energy. And so that's what you see down here at the bottom. And so when we call calculate, when we print the result, we get back this representation of the data set object. And so now we can start talking about actually manipulating this object, which we save as this calc result. And so if we call that, so we have the ability to do sophisticated indexing and selection into this. And so we have this iCell function, which allows us to select by index. And then we have this cell function, which allows us to select by coordinate value. And so if I do iCell and I write points equals 49, that means give me the result that for which points is at the index 49. So it comes in at the index being 49, but the literal value of it may not be 49. And then, but if I write cell, then I write t equals 1000, that means return the value for which t is equal to 1000. So that's the difference between cell and iCell. iCell is select by index, cell is select by value for the coordinate. So then if I just print that, we can see that this allows us to get back internal DOF equals 1. So that's the second internal degree of freedom at the point at index 49, selected for which the temperature is equal to 1000. So you can see here we computed at 2 different temperatures up here. We use this bracket notation, which allows us to specify a list that we'd like to calculate instead of doing a step. So the bracket notation lets us specifically say do this temperature and that temperature, if you know specifically what you want. And then if we access this values attribute, that lets us return any of these data variables back out as NumPy arrays. So if you need to convert a result to a NumPy array, you have the ability to do that. So that's how the calculate function works. So now we're going to go into the equilibrium results. And so it's pretty similar to calculate, but there's a couple differences. And so these first 4 are just like in calculate, except for multi-phase calculations, internal DOF is just the longest possible. It's the maximum of the internal degrees of freedom of all phases. And so that's the reason for that is so that the object can store all of the internal degrees of freedom for all the phases. So some phases have more internal degrees of freedom than others, and so for the smaller ones, those last values don't have any meaning. And so, but then we also now for the equilibrium calculation have some additional dimensions that are added. So in this case, we have this x underscore zinc, for example. So this represents the condition that was passed in to the equilibrium. So in this case, since we passed in mole fraction of zinc, then we will get back a mole fraction of zinc dimension. And so we can index into this dimension to access different parts of the calculation that we performed. And then we also have this vertex dimension. And so this basically gives us the index of the phase in equilibrium. So if we have equilibrium, there may be more than one phase in equilibrium. And so this allows you to index into, for a particular equilibrium, multi-phase equilibrium, we can index into a particular phase. So if you imagine we have 2 phases in equilibrium or 3 phases, then this vertex will be either 0 or 1 or 2, depending on which phase. Now the ordering of the vertex doesn't have any inherent physical meaning. So you just have to index into it and know which phase you want. And so that's made easier by the fact that we also have this phase data variable object. So we have the ability to index in and say, I just want the equilibria that have to do with a particular phase. And that's often the case. And then we have NP, which is the phase fraction of each phase in equilibrium. So this gives us the amount of the phase for a multi-phase case. And then we have mu, which represents the chemical potentials, x, which is mole fractions, just like before, y, which is site fractions, just like before, and then gm, which is the energy, the total energy of the system at equilibrium under the given conditions. And sometimes you'll also have additional outputs that you might have passed in. So for example, if I pass in HM, I will get not just GM, but also HM. So that's the molar enthalpy will be computed alongside. So I know that this is a lot. So the equilibrium object is very powerful, has a lot of features that you get back inside of the data set. And it may take some time, but it's okay because you have all this documentation information here, which is provided to you. And just as a reminder, you can always go back and right-click this workshop object and click download current folder as an archive, and you will save to your local computer all the files that you've worked on today. And additionally, you also have the ability to go to PyCalphad.org, and this will take you to our documentation, which has additional information here, and provides you more details about how to interact with the data. So you can click here, you'll get a very similar to the exercises we're going through now. And you're also welcome to contact us if you have questions beyond that. So one of the most powerful features of these dataset objects is this where function. So you have the ability to index into the phase fraction object and say, return the phase fractions where the FCC phase is present in equilibrium, and I just want the result where the pressure is 1 atmosphere and the temperature is 800 Kelvin. And we can see the result here where you get back the values. And so what the code does is you get back an object that has the same shape as the original NP array, but all of the values where this is not true have been masked off to and set to be not a number. And so this is convenient for working with, such that you can then take this data and plot it if needed or desired, and not have to worry about the results that are masked off. So, and again, if you have more questions about how to interact with this where object, there's the PyCalphad documentation, and there's also the X-array documentation. So here, this link in your notebook has more information here about indexing and selecting into data here. There's a lot of powerful features with this data set object, and I haven't touched on all of them today in the interest of time, but it's certainly a powerful feature. Any other questions? Okay, so I'm hearing none. I will we'll continue on now and talk a bit also about another powerful feature of PyCalphad, which is this the custom model capability. And so in today's custom model exercise, what we're going to do is we're going to build a CalPhad-based property model based on one that's been published in the literature and use it to predict viscosity in the aluminum copper zirconium system. And so there's been suggested a type of viscosity model called, it's a class of models called an entropy model. So it's a way of predicting viscosity based on entropy. And so it's kind of a nice natural connection to CalPhad because entropy is something that is very difficult to measure experimentally, but relatively straightforward for us to compute using our CalPhad-based models. So what we're going to do is we're going to calculate this excess entropy of the liquid term here. So this S term, which is key to the model. And the other thing that we're going to do is we're going to add a new parameter type, new sets of parameters to our database that are going to allow us to describe the viscosity of the pure elements. So that's aluminum, copper, and zirconium. So that's this eta term that's inside of this weighted sum. So we need a way to put those eta terms, which have some kinetic character in them and aren't purely characterized by this entropy. And so we need a way to put those terms in. So the way we might imagine is we'll write down this parameter type eta. Oops. We'll write this parameter type eta for the liquid and say aluminum, copper, and zirconium, and we'll write down this temperature function extracted from the literature and use it to describe the viscosity. And so in this case, we've already put those three parameters into the database for you, so we can see and go down here to here, and we can see, and the references are included for the viscosity terms, and so that would be sort of the first step that we would do in order to implement this model, but we have to do some additional work, as we'll now see. So if we try to load the database and run it, notice that we get this error. So when it tried to read the eta term, it failed out and gave us this parse error. And so why is that? So the reason is because eta is not part of the standard set of parameter types. And so the database tells us, it says, hey, you have this eta parameter type in here. I've never seen it, and I don't know what it is. And so we have to teach it. And so we need to tell PyCalphad's TDB parser that eta is an allowed parameter type. And so the way we do that is we reach into the internals, but it's officially supported. We reach into the internals of PyCalphad and update the accepted TDB keywords here. So this in our PyCalphad IO module, instead of TDB keywords, we have this TDB param types list. And so the parser checks this list to see if you have a supported parameter type or not. It's really just that that's the object. And so because we know it's a list, we can append to it and add this eta there, which we run that. And now when we run the database command again, now the database loads. Is there a question? Okay. And so anytime we define a new parameter type, we have to do this step appending to the TDB keywords module so that the PyCalphad knows how to read it. And it would also be necessary to distribute this little snippet of code in any scripts that would use the custom model. So this is part of the steps required for disseminating custom models. So we've loaded the database. So okay, it's great. So the parser knows that Ada is an allowed parameter type. It doesn't mean that it actually knows how to use it to build material properties. So for that, we have to write a custom model class. And so in PyCalphad, it's this model object that PyCalphad uses for both equilibrium and non-equilibrium properties. And that tells it how to compute all material properties. So that's in particular the Gibbs energy, but also other properties as well. And so if we want to build a viscosity model, we have to define a new subclass so that it knows how to use it. And so we have this important function called build phase. So build phase is a special function which is guaranteed to be called by PyCalphad when we build when this viscosity model object is initialized. And so generally speaking, you don't want to override the default init function for this because of some special behavior. So usually you just want to override build phase. And so inside of build phase, what we do is we call the parent model. And I apologize if some of the syntax is unfamiliar to you, but this is standard syntax for dealing with inheritance inside of Python. So if you have questions about how this works, you can look up the super built-in Python method, which can provide you a little bit more information. But what we're doing here is we're basically just saying, call the build phase of the default built-in PyCalphad model. So that tells it, hey, this isn't a completely clean slate phase model that we're building. We want to build all the existing models. And then what we want to do is we just want to define our custom viscosity property on top of that. So we assign a new viscosity attribute to our model. And then later on, we will tell PyCalphad to look for this attribute to build our phase. So we say, define the viscosity attribute, and then call our new custom build viscosity function to build the viscosity. So here, that's what we wrote, except we're not doing all of it yet because we're saying, oh, wait, we have to figure out how to actually write our build viscosity function as well. And so build viscosity has to do 4 things. We need to query the database to get all of the Ada parameters. We have to compute the weighted sum relative to the composition of the liquid. We have to compute the excess entropy of the liquid. And then we need to plug all those values into our equation up top and return the result. And so our build viscosity function needs to do all of this. And so there's a lot of steps here to take. And so what I did was I labeled each one of the steps from above. I labeled them with a comment here. And so the first thing we do is we check to see that our phase name is actually liquid, because in this model, we don't know how to define the viscosity of solids. Then we define a phase object. And so we extract the phase object from the database, which makes it more convenient to work with. And we also assign this name param search to the built-in search object. So the search function is like the querying of the database. And so first we have to query the database. So we have to write a query. And so here we're using the where function from TinyDB. So this is a slight implementation detail. So remember, the custom models are a little bit more advanced. So we're reaching a little bit more into the internals of PyCalphad when we do this. And so we're writing a query and we're saying, get all the parameters where the phase name is equal to, the name of the current phase, where the parameter type is equal to Ada. So this will just return us the Ada parameters. And then where the constituent array is passes this test. So this built-in array validity function, which is defined on the model. And so this is a little, you can kind of treat this as boilerplate, but what this does basically is it filters the parameters such that you only get parameters for the active components. So for example, if I do an equilibrium calculation for aluminum copper, I don't want to get back any parameters dealing with zirconium or any other component that's not in the active set. And so that's what this function down here does. It also does things like make sure that you're getting the correct interaction parameters and things like that, and checking some other details like that. So it's good practice to include this. And then next, to compute the weighted sum, we can leverage our built-in Redlich-Kister sum function, which is built into model. So we just pass in the phase, we pass in this the param search function, which is just the built-in database querying thing. And then we pass in our query, which is defined right here. And so the thing that we get back is it's a SymPy symbolic mathematical representation of the first term here, this weighted sum of the etas. So that is what is contained now in this eta object. So that's the first two steps. And then for step 3, we need to be able to compute the excess entropy. So first we need to compute the excess energy. And so to do that, what we do is we take the Gibbs energy. So this Gibbs energy attribute GM is defined in our model. So remember, we still computed all the default properties above, but then we subtract out this reference. So this has to do with the pure components. So energy contributions from the pure components. And then we also subtract out the contribution from ideal mixing. And so some of this might look like I'm using magic strings. And you're correct, I didn't define them above, but they are defined in the documentation in the model object. And so if you need information about what contributions map to where, you can look at the model object, or in some cases refer actually back to the model .py module. In some cases, you may need to do that depending on the calculation that you're trying to do to make sure that you're doing the right thing. So this gives us the excess energy, but I want the excess entropy. So then the entropy, we apply the thermodynamic definition where it's equal to the negative of the temperature derivative. So again, these are symbolic mathematical objects here powered by SymPy. So I take the excess entropy, I can take the negative of it, and then I can call this .diff. And so this is, like you might think, this is symbolic differentiation of the object with respect to temperature. So it's our temperature object there. So that will return back to you the negative of the temperature derivative, which is the entropy. So that gives us our excess entropy. And then finally, we put it all together, and we are able to calculate all the terms in this equation. And then finally, we return the result here. And so I also here assigned to an eta attribute, and so that just gives us the weighted sum. That's really just more for debugging. I'm not particularly interested in that quantity, but for debugging, you can also assign attributes for intermediate quantities in your calculation, and that can make it easier as you're developing the model to go back and check to make sure everything works. So I know that was a lot, but let's put it all together, and then I'll take some questions. And so we can compute the. Oops, I forgot to run this this cell here. So where we actually define the build viscosity function, and now we call it, and so we've built our viscosity model, and so now we have the ability to actually put all this together. So we're going to call our calculate function just like before, but notice we pass this keyword argument, model equals mod, and so that tells it to not use the default model object, but to use our custom subclass. And then we also specify that the output is equal to viscosity. And so what that means is we're telling it to not take the default GM attribute, we're telling it to take it matches up here with this viscosity. So it basically just looks for the output keyword argument tells it to look for an attribute on the model that has this name. So it'll just look for the viscosity attribute of your model. And that's how that works. So we do that calculation. We'll do it at 2100 Kelvin. And then we plot the result as a function of the zirconium content. And so we can see here the viscosity, and it has the shape that's expected. You can compare to some figures in the original publication and see that we're getting consistent results here. And then we can do the same calculation also for the aluminum copper system at 1300 Kelvin. And you can see here we also get expected behavior for the viscosity. Note that this model is strictly only valid for small undercooling. So you can't use this to do something more sophisticated, like study the glass transition. Not directly with this model. You would need to develop a more sophisticated model, but that is possible to do using PyCalphad. So that's the custom model one's probably our most sophisticated example today. But I'm happy to pause and take some questions if we have them. Okay, hearing no questions, I'll continue on now to the multi-component example. And so I don't talk a whole lot in detail about this example. I just want to show you that PyCalphad is not just for binary and ternary systems. You can also use it for multi-component. In our current cloud deployment, probably only about maybe 5 or 6 component systems will work due to memory limitations. Though if you're running on a local machine, you'll have less memory limitations. And also, we are continuing to do work to improve the memory efficiency of PyCalphad, such that in the future, even with very modest RAM, you'll be able to run complex multi-component systems with 10 or more components. And so in this case, we're going to do a steel example. Excuse me. We'll do a steel example. And so this is based on an open database from MatCalc for steel-based systems, which has been slightly modified to work with PyCalphad. We also have PyCalphad compatible versions of all of the MatCalc open databases, including aluminum and nickel, though not all of them are in your database folder here. Feel free to reach out to us if you're interested in that. We do have it publicly available on the PyCalphad GitHub. So we're running now, and so I'll just mention. So we have the ability to write not v.x but v.w. So this refers not to mole fraction but to weight fraction. So you do have the ability to write things in terms of weight fraction, which may be more convenient or intuitive for certain systems. And then what you do is you then call this get mole fractions function, which will convert from weight fractions to mole fractions for you. And then you use that as part of the conditions here. Also, again, because of this memory limitation, we did slightly adjust the point density of the calculation and turned it down a bit, which helped. That's a detail that may or may not be necessary to you, depending on the system that you're running on. It just turned out to be necessary for this cloud deployment that we're doing here. So this may take some time, so several minutes to run this step calculation, but I'll just show you the result here that we're able to get and plot the phase fractions versus temperature. And so we'll see here it does look a bit interesting. We're seeing some BCC stability in a region that you probably wouldn't expect for steel. So this composition is actually simplified slightly from 316 to deal with a reduced number of components. And so you would expect actually to see a bit more FCC stability, in the case of the actual 316. but it is illustrating that we're getting largely the expected behavior. We're seeing the phases that we would expect to see that are stable at the temperatures we would expect to see them at. So this is for the phase fractions versus temperature. We also can plot the compositions of the phases versus temperature. So in this case, we're interested in the sigma phase, so we can plot the composition of these different constituent elements and plot the mole fractions versus temperature. So you see here it's cut off. That's because you only get the phase compositions where the phase is actually stable. And then we can do the same thing also for the FCC phase. Yeah, I know there's a lot of complicated array management that's happening here, but one of the nice things about having these examples is you can copy them and edit them for your needs. And in fact, this is what I often do when I start a new calculation in PyCalphad. Is I usually go and find the closest example I can, and then slightly modify it for my needs to do this. You may also discover some of these examples were written before for older versions of Xarray, and many of the indexing and querying features of Xarray have improved considerably. And so what you might find actually is that there is a newer way to do some of these post-processing steps that requires fewer lines of code. And if you do find such a case, we'd be delighted to learn about it and contribute to these examples. So I'll pause again for questions in case we have them. A good place to find these multi-component databases I mentioned is on our binder. We have collected some additional databases here, which have been either confirmed to work with PyCalphad or have been modified slightly to work with PyCalphad. Please note we don't confirm or guarantee the accuracy or appropriateness of any of these databases for your use case. We haven't done independent validation of them. They're there for illustrative purposes only. But we would be interested to hear your feedback about them if you have any experience with these systems or find a result that is surprising one way or the other. We would be interested to know about that. Okay. So now to touch on this last example here. So this is for calculations with reference states. And so by default, the energies that you compute in PyCalphad are relative. You can think of them like an absolute energy, although it's a little bit of an oxymoron. You can think of them, they're energies that are defined relative to a reference state that is inherent to a given database. And so that reference state is not promised to be anything in particular. And so if you want to do computations with respect to a particular reference state, you have to be explicit with that choice. So when you are explicit and you call the shift reference state method, you will now get new properties that are defined relative to the reference state. So instead of GM, you have GMR. Instead of HM, you have HMR, and so on. And so the R suffix tells you that it's with respect to a new reference state. So we're going to do an example here where we compute the enthalpy of mixing in the liquid. So it's kind of analogous to what you might measure experimentally. And so we want to specify a reference state with respect to the whatever the calculation temperature is. And so we now import this reference state object, and then we specify a reference state for the component and then the phase, and then we we collect these reference states together into a list. And then we have to do a little bit of custom model work here. So this is kind of analogous to what we were doing before with the custom models. They're simpler. We create the default model, and then we call the shift reference state object on, and then we pass in our desired reference states and then the database. And then we pass our modified model in to calculate. And so the way the reference state capability works is it's basically kind of like a custom model that that does the reference state math for you, so that the property comes out in the with the right reference state. So we call calculate with this. We want the output to be HMR, so that's the enthalpy at the reference state. And of course, the key part is we define our custom model there, and then we do some matplotlib work to draw the result. And so we can see here the mixing enthalpy, right? And so you see the mixing enthalpy is 0 at the pure component end members here by definition. And we see that that's correctly reproduced here through this reference state shift. A little bit more of a complicated or advanced case here is we can fix the reference state and not allow it to float with the calculation temperature, but fix it for a particular temperature. So for example, we can fix it at 298 Kelvin and 1 atmosphere for these particular phases. And so in this case, these would correspond to the standard element reference for these elements. And so we can specify those. And then now here we do the same thing we did before, except we wrote a for loop to take care of shifting all of the phases in this database to be relative to this reference state for niobium and rhenium. And so that's all that's happening here. It's the same thing that happened before, except we're just calling a for loop for all the phases. And then we're going to once again calculate the reference enthalpy or the enthalpy at this reference state, and include this keyword argument for the models as well, which is essential for the custom reference state to work. And then there's a little bit of funny array math that we do in order to make this nice plot appear. And so this has to do with grouping all of the phases that come from the same set of equilibria together. And so the purpose of that is so that we can color code them. And so you get this nice plot showing, more or less corresponding to phase transitions as the rhenium content is increased. So we can see starting off with just liquid, and then we go into a region that has liquid and sigma in coexistence. And then there is another change with sigma and chi phase. And then what you'll notice is each time, in some cases, there's a kink in the curve, right? So corresponding to a phase transition that's occurred. And so that's accurately reproduced here. So this is a nice way to visualize equilibria for your system, and may make it convenient to compare with experimental data in some cases. We also include a special reference state because of how common it is to be interested in mixing. We also provide a mixing reference state, which is just reference with respect to the end members for that phase. So this can be useful, particularly for studying multi-sublattice phases or phases with internal degrees of freedom. So you can see here, we don't have to do reference state stuff here. We just have to specify the HM_mix and then plot the results. And so now we can see how all those end members have been shifted such that their enthalpies are 0. And so that that distorts the plot here, like you would expect a reference state transformation to. We also have the ability to do calculations at specific site fractions. So if you want to control the particular degrees of freedom that you're interested in, we provide here the information about how to order the internal degrees of freedom in the array. So they're basically alphabetical by sublattice. So you alphabetically sort the first sublattice and put in the degrees of freedom, and then the second, and so on. And that's the ordering. And so you can specify those site fractions and then pass those site fractions in using this points keyword argument, and you will get not a random sampling of the internal degrees of freedom, but you will get just the site fractions you are interested in the order that you pass them in. So then there's a one-to-one correspondence between the array that you passed in and the output properties. And so this can be useful for doing just selected calculations for just a certain degrees of freedom. This is particularly useful for like a multi-component system where you don't necessarily want a random sampling of all the internal degrees of freedom. You're just interested in maybe one particular subset. And so this is the conclusion of the structured part of the PyCalphad session. So I'm happy now to pause and take any questions that you may have about PyCalphad.
Can all of you run the calculations along with Richard? Oh, there's one question there in the chat.
So where do we get the databases? So one place is you can make them yourself. So we'll learn about how to do that today using SBay. But I recognize that sometimes you don't have that kind of time, depending on the system that you're interested in. So one of the places you can look, which we touched on a little earlier, is the TDBDB. So this is an indexing service run by Axel van der Wal at Brown University. And you can go here and it provides an index. So for example, if you're interested in iron oxygen, you can look up and see a pretty good selection. It's a fairly comprehensive index. They try to get and touch on as many as you can. And so this is often a good place to start. And I also showed earlier that we have some, if you go onto our binder repository, we do have a few additional multi-component databases available as well that may or may not be suitable for your application. You should take a look at them and validate them for your application. So that's what we typically recommend currently for databases. And so we have a question from Tessa. Hello, Tessa, asking about second order phase boundaries like magnetic transitions or spinodal boundaries. So we don't have an example in the workshop today. We have previously used, we do have the capability in PyCalphad to plot the magnetic transitions. And so for magnetic transitions, the way that you do it is you do a little bit of a trick. So you would compute the Curie temperature as a property, and then you would map it over your whole phase diagram, and then you would look for sign changes basically, or excuse me, you would look for where the temperature on the phase diagram approaches the calculated Curie temperature, because that indicates that you're at the transition point. And so that would be how you would do the magnetic transitions. It's a little strange, but actually in the 2017 PyCalphad paper, which is cited in the PowerPoint slides in the PDF we provided you, we actually have that example, and I think the code is even in the paper. Although I think it's in the paper as an image, unfortunately, but the code is there, and kind of shows you how you might do that. For the spinodal, it's a little trickier. The way that you would need to do that is you would probably have to compute the stability function yourself. So you would probably take a random sample of the energy surface, and then you would have to compute the stability function and then look for sign changes. And then when you find a sign change, you would plot that on top of the phase diagram if you wanted to superimpose it on the phase diagram. But that's actually been a fairly popular question recently, and so that we may need to develop an example talking about the spinodal, but it is possible to do with PyCalphad. It's just a little bit of work to compute the stability function, but we have the built-in capability to do that. You can compute the second derivatives, and then you can compute the eigenvalues, and then you just have to look for the sign change, and that's how you would do it. But unfortunately, I don't have a ready to go example here, and it would probably take me like I would say typically maybe like an hour or two to put that together, and that's when I'm not in the fishbowl with people watching. But I'd be happy to have follow-up conversations about that if that's an interesting direction for you. Any other questions? All right. Well, I appreciate the opportunity to present PyCalphad to you guys today. And please reach out at the contact information in the PDF slides if you have questions. And also, don't forget today about taking your work home with you by using these download features. And so I think now probably what we will do is we will take a maybe about a 15-minute break, and then pick it back up, or do we need to come back sooner, Brandon? What do you think?
I think starting on the hour is good. So about 15 minutes.
Okay, great. All right. Well, thank you guys, and let us know if you have any other questions.
Yep. So feel free.